Welcome back, everyone. We're talking about Chapter 4, Winds and Pressure. This is going to be divided up into several parts. So this is Part 1. Okay, the atmosphere, as we can see in this diagram here, extends way up into, or way above the ground. We say about 60 miles or so would be the classic differentiation between what is atmosphere and what is outer space. So we're looking at the possibility that beyond 60 miles, that's astronomy. Below that, that's geography. On the diagram you see here, we have on the left axis altitude in miles. We can clearly see that with the lower axis, the horizontal axis, we're looking at percentage of sea level pressure. So if we start at 0 miles above sea level, that means at sea level, we have 100% of the atmosphere above us. If we go up to about 4 miles, we only have about 50% of the atmosphere above us and 50% below. Go up to about 16 miles, and we're looking at 95% of the atmosphere below that level and only 5% above. And the reason for that is all the molecules in the atmosphere are crushed down towards the bottom due to the force of gravity. We can see that, or we know from experience, if you're at sea level and you're experiencing sea level pressure, that's a lot more pressure than if you go to the top of a very high mountain like the top of Mount Everest. In that case, the air is quite a bit thinner because the molecules from the upper atmosphere pushing down, well, there's a lot fewer molecules above the top of Mount Everest than there are above, let's say, Bombay or Mumbai in India. Now we can measure the weight of these molecules pushing down on us through a device called a barometer. Well, the Latin word for atmosphere is bar. So this is an atmospherometer, a barometer, invented by Torricelli in the 1640s by basically utilizing a huge tube of water and seeing what the pressure of the atmosphere was, being able to measure the weight of the atmosphere. That tube had to be about 34 feet long at least. These days, instead of using water, we can use a substance that remains liquid at most temperatures on the planet. So we use mercury because mercury is about 14 times heavier than water, and therefore we don't have to use a tube as much or as tall. In this case, we would take a tube filled with mercury, stick it into a big tub of mercury, turn it upside down, release a stopper, and basically we would see the level drop from, if this was a full container before, or a full vessel of mercury, it would drop down, creating a vacuum up here at the top. Now, however high that level settles out to, measured against the liquid still in the tub of mercury, that distance right there, or that measure right there, would tell us something about the weight of the atmosphere. If the atmosphere was pushing down with a little bit more force, this mercury would rise higher into the tube. If the atmosphere was pushing with a little less force, the mercury in this tube would go down. Well, if we took this device to multiple places around the planet and added up or found the average, we would see that this level right here would average out at 29.92 inches. So the average atmospheric pressure throughout the planet at sea level is 29.92 inches of mercury as measured by a mercury barometer. But we're going to see in a second there are several ways of measuring that. But for now, I want you to stop and think. What would make that level go higher? Assuming we're still at sea level. What would make that level go lower? Well, the obvious answer is if air was pushing down more, the height of the mercury in that tube would go higher. So if the atmosphere was sinking, if the atoms in the atmosphere, the molecules were sinking down, so if air was sinking down, we would see higher atmospheric pressure. So that's, again, an association I want you to be familiar with. If air is sinking, we're going to get high atmospheric pressure. And conversely, if the air was rising, we would see lower readings on the mercury barometer and therefore lower atmospheric pressure. As I mentioned, we have the average atmospheric pressure at sea level, basically measuring the weight of all these molecules pushing down. The average of that, 29.92 inches of mercury. You see here the symbol Hg That's the chemical symbol for mercury. And again, 29.92 inches of mercury is average atmospheric pressure at sea level in inches of mercury. Now in Europe and other places, we don't use inches so much, we use centimeters and millimeters. So the same tube could be measured in centimeters of mercury, and the average would be 76 centimeters of mercury. Now for every centimeter, there are 10 millimeters. So if we have 760 centimeters of mercury, that's the same as 760 millimeters of mercury. So already 3 measurements that you need to know: 29.92 inches of mercury, 76 centimeters of mercury, and 760 millimeters of mercury. You'll see these in different places throughout the world. We could also measure the atmospheric pressure of all these molecules pushing down on the surface of the Earth in terms of how many atmospheres we have. Well, the obvious answer here is if you're at the surface of the Earth, you only have 1 atmosphere above you. If you're about 4 miles up above the surface of the Earth, you would have about a half of an atmosphere, the weight of an atmosphere, above you, because half the molecules would be above you at that point and half the molecules would be below you if, again, you were 4 miles up. Now, the only time that really changes near sea level is if you are at the surface of the Earth, you have 1 atmosphere of pressure on you. But if you go scuba diving and you go down about 33 feet of seawater, you would have the weight of the atmosphere plus the weight of that 33 feet of seawater, and that's the same as 2 atmospheres of pressure. If you went underwater even further, you went to 66 feet below the surface of the sea, you would, let's say if you're scuba diving, you would experience 3 atmospheres of pressure. So that's about the only time in most of our lives that we might be talking about more than 1 atmosphere above us. I mentioned it before, in Latin, the word for atmosphere is bar. So you have 1 atmosphere of pressure or 1 bar. Another measurement is in terms of pounds per square inch, or PSI. So every square inch of our bodies has 14.7 pounds of pressure pushing inwards. So that's a lot of measurements here. The very bottom one, though, 1,013 millibars. Well, milli means 1,000th. So 1,000th of a bar. We've already looked at 1 bar, 1 atmosphere. So if we broke that down into 1,000 equal portions, that should be 1,000 millibars. But we do realize with more accurate equipment that our atmospheric pressure is really just over 1,000 millibars. It is in fact 1,013.25 millibars. So all of these are average atmospheric pressure at sea level. And it's all due to gravity pushing downwards and crushing all those molecules down towards the surface of the Earth. Now, might be hard to see on this diagram here, but there are certain numbers, and those numbers are representing millibars of pressure for a portion of the United States back in the year 2000. And we can see numbers like 1,013, 1,014, 1,025, 1,026. These are all measurements at the very same time from various weather stations. Now, we don't have weather stations every single house in the United States or every single building. We don't need that many. In fact, we can take measurements in certain places and we can interpolate what the pressure is in between those stations. For instance, if we look over here, here we have 1,013 millibars, here we have 1,013 millibars, and here we have 1,017. We know that somewhere in between there, the pressure slowly increased. So we put these lines around, and these are now computer generated, they used to be hand generated, and these lines would say, in particular the one I'm highlighting right now, in fact if I double click this one, no, it's not going to happen. Okay, on this one right here, everywhere on that line would be representing about 1,014 millibars. Let's say the next line over here. Anywhere on this line would be 1,018 millibars. And the next one, 1,022 millibars on this line here. If you can see in this case, that line splits between the 1,023 and the 1,020. So someone has drawn the line thinking, about here's where it would be 1,022. These lines where it's equal pressure, those are referred to as isobars. So iso means equal, bars means atmospheric pressure. So these are lines of equal atmospheric pressure. And these can tell us exactly what the pressure is, or about what the pressure is, for pretty much any place on the planet that we have enough data points for. Another thing it tells us is that you see this line here, 1014, and over here 1018. The distance between those two is pretty big. That means it's taking a long time for that pressure to change. Whereas on other portions, for instance over here on the upper left, between these two lines, those two isobars are not that far apart in terms of actual distance on the ground. That means the pressure is changing a lot more quickly from one to the other. So if the isobars are pretty far apart, that's going to tell us one thing. And if the isobars are pretty close together, it'll tell us something completely different. That thing is expressed on this map also. So we're looking at isobars here, where these lines are pretty close together. That means the atmospheric pressure is changing pretty quickly compared to places where the atmospheric pressure is not changing as rapidly. That means that the airflow between those two areas is not going to be very quick. What that relates to is this diagram here. If the isobars are pretty close together, that's going to give us pretty fast wind speeds. If the isobars are pretty far apart, that's going to give us pretty much slower wind speeds. So again, isobars closely spaced, winds are fast. Isobars are pretty far apart, that's going to mean that the wind speeds are pretty slow by comparison. Again, another way of looking at this, we often look at air pressure from maps, as we did in those prior slides, by looking down onto the surface of the Earth. So the lower portion of this diagram here shows a map view or plan view. We're looking down as if we were on a satellite, looking down towards the surface of the Earth. And what we're seeing here is pressure going from 1020 to 1019 to 1018 millibars. And you can notice here that the air is tending to move from high pressure to low pressure. Well, that's following a force known as the pressure gradient force. And that says air must move from high pressure towards low pressure. Well, the way to visualize that in the upper diagram, the exact same thing, it's showing that when we have high pressure, so this portion of the diagram here is a cross-section view, like we're looking across the landscape instead of looking down. And what we're seeing is a lot of molecules here, a lot of extra molecules that have accumulated at the surface. That's where we'd have 1020 millibars. And the air is moving from there towards the right, in this case, towards an area of lower pressure. So imagine these air molecules are sort of like marbles that are being stacked up. Here we got too many marbles stacked up. Over towards the right side of the diagram, not enough marbles. Hasn't stacked up very much. And if this is shaken a little bit, if the system is disturbed, what's going to happen is the extra marbles are going to move from left to right. Well, instead of marbles, you know we're talking about molecules of air. They're also going to move, in this case, from high pressure to low pressure, following that pressure gradient force. So what does the pressure gradient force say? Basically, air has to move from high pressure to low pressure. Well, let me rephrase that. Air has to try to move from high pressure to low pressure. Again, air will try to move from high pressure to low pressure. Now, if the isobars are pretty closely spaced, that means that the pressure gradient force is pretty strong and air will move pretty quickly. Whereas if the pressure gradient force is not so strong, if it's pretty weak, in that case, airflow will still go from high pressure to low pressure, but it won't be as forceful, and therefore you're going to get a slower wind. Now in this diagram here, we're showing a cyclone and anticyclone. When you see the word cyclone, I want you to be thinking about an area where air is rising. And when you see the word anticyclone, I want you to think about an area where the air is sinking. There are all kinds of associations to learn about this. For instance, this diagram, to get this into your head, as the air is rising, it's going to be cooling adiabatically. It's going to release at some point, if it rises high enough, its water vapor into the form of water droplets. Light will bounce off of those and we'll see a cloud. If the cloud gets big enough, we might get rain. So rain, clouds, rising air, adiabatic cooling, all associated with low pressure at the surface, so low surface pressure. And we measure all of our atmospheric pressure that we're going to be talking about at the surface. So this is referred to as a cyclone, an area of low pressure. On the other hand, an anticyclone, the opposite, is an area of sinking air. Now, the only way we can get to ever form clouds is by having air rise, like in a cyclone. If we have air sinking, we won't get clouds. In fact, we'll have clear skies. So clear skies associated with sinking air, that air will warm adiabatically on its way down and then spread out in all directions. And this is a classic anticyclone. Sinking air, warming adiabatically. Now to get a little bit more in tune with this, there's a little animation I've done. You have the link for it under modules. I believe I've called it video 4-1. I would like for you to look at that, and then we will regroup after you've learned a little bit more about cyclones, anticyclones, and their associated weather. That's the diagram you'll be learning about. Okay, see you soon.